Hey, Mr. Sams, how you doing?
Not too shabby.
What are you doing? Oh, you're making a mess.
Sorry, it's my desk. It's
Yeah,
all right.
that's true.
You're
drinking some 7-Up. I see.
Yeah.
That's interesting.
Ooh, it's diet.
Diet. Woo.
Oh, I hate diet soda.
Why did you buy the diet?
I don't. You did. It was for our workshop last week.
Oh yeah. Well, I didn't drink it. I don't drink the soda. I just buy the soda. Hey, today we're going to learn about electrochemistry.
Yeah.
Now what are you doing, Mr. Sams?
Well, that's why I'm having a soda.
You're having a soda? Now I wonder if people can see what you're doing.
Maybe.
What are you doing there? Oh, it's like an experiment.
It is. Look
Check
at that.
it out. We have an experiment, people.
So I got
Mr. Sams has an experiment. Electrochemistry has to do with like electrons.
It does. Yeah.
And like electricity.
Moving. And if I get enough electricity, I can make my clock work here.
You have a clock.
Yep. No, it's not working right now.
Mr. Sams, I thought you said it was going to work.
It will. Well, I've got
a
little copper electrode here. Okay.
Yeah.
And I've got a zinc one here.
I see that, yeah.
Okay, but the problem is these two cells aren't really linked to one another, so I'm actually going to take some more copper,
some more zinc. Yes!
We're going to go the other direction.
We call that, in chemistry land, folks, a salt bridge.
Yeah.
And guess what? I believe it's 2 o'clock.
Is it?
Or noon o'clock.
Noon o'clock. Look at that. My clock works. Can you see
made
that?
a clock.
Isn't it amazing?
He's amazing. A clock with some soda.
Yep.
So you can get electricity out of a can of soda?
Yeah, well, we're not really getting it out of the can. What we're really getting it out of is these little metals right here.
Oh.
Because what's happening is we have a redox reaction going on.
That's right.
And as a result, there's some electrons that are moving, because on redox reactions, there's always an exchange of some electrons. Something is being oxidized and something is being reduced. So either the copper is being oxidized and the zinc is being reduced, or the copper is being reduced and the zinc is being oxidized.
That's right. And so we're going to have to figure that out as we go, folks. And so we will. So today, we want to do a little bit of review of redox, because something that Mr. Sams just mentioned as you watched the podcast or watched the demonstration was that electrons are moving around, and because it's a redox reaction, and if we can harness those electrons, we have electrochemistry. Electrochemistry.
I still have a really gross taste in my mouth from that diet.
You picked the wrong one. Okay. Yeah. Hey, let's just do a real quick review. We learned a long time ago about oxidation numbers, and we need to kind of do a little review.
Yep.
So, what are the oxidation numbers of H, N, and O in HNO3?
Well, I know H's are almost always +1, unless it's a hydride, which is very rare. And oxygen's almost always -2. Now, we also have 3 of them there, so that's going to be -6. And they always have to add up to 0 in a neutral compound.
Therefore?
So, it's looking like X is going to be +5.
Same thing, and then this one...
And that would be nitrogen, by the way, the X.
Oh yeah, X equals the charge of the nitrogen. And you would say N +5, O -2, and H +1. So they would each have a different oxidation number.
There you go.
We can do lead sulfate as well.
Yeah.
Now, actually, the hard one will be which?
Well, if I look at this, this is lead 2 sulfate, because sulfate is a -2 charge always, and so lead's going to be +2.
So PB is +2, and we know O's charge is -2.
And
so the only one that's mystery is kind of that S.
Yeah.
Right?
And
so that'll be 2 plus what? X plus -8
right.
equals 0.
And it's -8 because there's 4 of the oxygens.
So S is +6.
6, yeah.
Now, I'm not going to do big math, folks. You can do that. You know what? I think you could figure this one out.
Yeah.
We're not going to do it.
No.
All right. Hey, just remember how we balance oxidation reduction reactions.
Yep.
Just a little do by
half reaction method.
Half reaction method. So I'm going to take the aluminum. I'm going to have the aluminum go to aluminum plus 3. And that's 3 electrons on the other side.
I'm going to have to take your word for it that that's what that says, because I just had I had an eye exam.
It says it, yeah.
And my eyes are all dilated, my pupils are dilated, and everything's all blurry.
Well, you could look at that thing there, and we could like bring that back, and we could look at your eyeballs.
That's true.
And,
are they big? Can you
tell?
tell?
My gosh! So the permanganate.
You got a new toy. Can you tell?
Goes to Mn +2. Now you balance your waters or your oxygens with water.
With water, so we need 4 H2Os.
4 waters.
Yep.
And then on the other side, I have to do the 8 hydrogens.
Uh-huh.
And then when you say this side here is +2, this side is +7.
So we need
5 electrons. That's a 7. Doesn't look like 7.
Yeah.
All right, and multiply this one by 5. And this one by 3. So it'll be 5 ALs plus 24 H positives. I guess I should say AL.
AL, there you go.
Plus 3 permanganates makes 3 Mn2 positives plus 12 waters.
Yep.
I got some aluminums left.
And 5 Al3 positives.
5 Al3 positives.
There you go.
Okay.
Okay.
Now in a basic medium,
solution.
Same ball game.
Yep, to start with.
This is a good one here, this first one. Mg goes to MgOH2. Now on this one, since it's in a basic medium, we actually can just say, well, that's hydroxides here.
Yeah.
And there's like 2 of them.
Yeah.
Done. Oh, is it done?
No.
Charge issue.
Yeah, charge issue.
Got to bounce the charge. Lee, are you bouncing the charge?
Better check.
All right,
2 electrons.
Check
There you go.
Lee. Okay, and then we've got the OCl negative, and that goes to Cl negative. Now my Cl's are good.
Yeah.
So now I'm going to balance the O's with water, and I'm going to have to put 2H positive on this side.
Yep.
But of course we're not in an acidic solution, so we're in a basic solution. So I'm going to add
2 hydroxides to both sides to get rid of those H pluses. And the H plus and the OH minus, those become 2 waters.
This is 2 waters.
Okay.
And the 1 water here cancels off the 2 waters to make
1 water.
1 water on that side.
Yep. And we've got some charge.
Charge issue. This side has a charge of -1, the OCl negative. This is -3, so I'm going to need an additional 2 electrons on that side. And oh my!
Oh, 2 electrons and 2 electrons.
I got lucky on that one, didn't I?
Yes, you
now we do have an
did.
issue here. Is we have 2 hydroxides on this side and 2 hydroxides on this side, so they just go away.
Bye bye.
Okay. And anything else canceling? I think we're good. The waters.
The electrons
no, I
always
think we're just
will.
good. So it'll be Mg plus OCl negative.
Yep. Plus H2O.
Plus 1 water makes the MgOH2 plus the chloride.
Yeah.
Bingo.
So if I put magnesium metal in bleach, I get magnesium hydroxide and chloride on it?
Yes, you do.
Cool. Balance the following redox reaction, the big nasty problem.
You know what? You have big nasty problems in the answers or in the podcasts, and I did an answer podcast for that, so you guys can figure this out on your own. Okay.
Yeehaw, we're going to save your time here.
Okay. Review of redox reaction. What's oxidation?
That's when your oxidation state goes up.
So oxidation
It becomes more positive, I guess I could say.
goes up.
Yep, and you lose electrons. That's how that happens.
By losing electrons.
Yep.
And reduction is when
Oxidation state goes down by gaining electrons.
All right, how do you make a, here's a fancy word here, folks. How do I make a battery?
Don't
Now,
you just go to the
scientists,
store and buy them?
You could, but you know, batteries. We made a battery just a little bit ago. That's your clock.
Oh, that's right.
All right. So if you want to look at a battery, Mr. Sams is now looking at a battery.
Yeah.
See the battery. All right. But
it's
scientists
amazing.
don't use the term batteries. They
No.
call them
Galvanic cells. 'Cause that's
which
what
are a battery. Actually, that's as I wanted to say.
Yep.
This was supposed to say galvanic here, and this is a cell.
we just don't remember what our notes are supposed to
and
do.
that is a
That's
battery.
okay.
So we can make batteries, folks. And you see, batteries are simply a mixture of chemicals.
We can make them with the disgusting diet soda.
Yes, indeed. Or, you know, we could even make it with an orange.
We could make it with an orange. Just stick it in there.
Okay. Now, if you
right.
think about this, actually, let's go back a piece to one of these reactions that we just did. Let's do the easy one here. Well, it's not easy. But here we had electrons.
Mm-hmm.
And maybe we should say one other thing here. I got it now.
All right.
You see, when you have one of these reactions where electrons are, something you may not know, and I want you to write this down, I don't think we put this in the notes, is that, what is electricity?
Electricity is just moving electrons.
That's the key thing. Electricity is moving electrons.
Yep.
And so if somehow we can capture, so when we have a redox reactions, you know, on one side I produce 3 electrons, in the other half reactions I have 3 electrons. If somehow I could have these electrons travel through something,
Like a clock.
like a wire or whatever, you can have the electrons do some work for you, like make the clock work,
Exactly.
or something of that nature. And so I want you to understand that electricity is simply moving electrons. So everybody look at the light bulb that is probably on in the room that you're at. Realize that electrons are actually moving through wires, and it's doing some work and producing light. Conversely, you're watching an iPod or you're on your computer or whatever. Electrons are moving through your computer or your iPod or whatever it might be, and it's doing work. It's producing light. It's also being converted to sound, etc. And so that's how this all works. So hopefully they understand that. We want to somehow capture the electron. How do we do that? All right. The way we do that is we need to make a separate cell, or you might think of the cell as a container.
Yeah,
like
a cup.
Yeah, for each half reaction. All right.
By the way, can I just tell you for a second, we're kind of lying to you. These aren't actually separate half reaction cells. These are actually two separate batteries in here.
Yeah,
but we'll explain that later.
All right, now here I have a particular system where, for example, I've got copper sulfate in one cell or one container, a beaker of some kind. And on the other side, I have zinc sulfate. I have a piece of copper. It's hard to see here. There's a piece of copper and also a piece of zinc. And this will make, and this galvanometer is like a voltmeter. It measures how many volts pass through it. All right. Now there's something missing though. There's a problem with this particular cell. Mr. Siemens, what is that problem?
Well, it looks like we're missing the salt bridge.
So you need something called a salt bridge. And what happens for that is that this allows the ions to move through your cells. So you need to kind of make a note of this.
Electrons are negatively charged. If we just let the electrons move through, we'd get this real big buildup of negatives in one side.
It kills the
cell. And things in nature don't like to be polarized like that. They like to be balanced. Right. So to do that, we're going to have to relieve the negativeness of one of those cells.
So here's the actual picture if you look down here. Here's the salt bridge so that the ions can flow. So if you put a salt
lime in the coconut. Oh, sorry.
The cell will produce voltage or electricity for a long time.
Put the lime
in the coconut. Okay. Now another way that you can do this, the picture we have, sometimes the salt bridges can look a little bit different. You could actually have the salt bridge.
The porous disc salt bridge.
Yeah, it's a different kind. It's actually easy to draw, frankly. You could have one right here, and then right through here we have something called, those little things are called a porous, P-O-R?
O-U-S, I think.
O-U-S disc.
Yep. It's just a chunk of ceramic.
A little piece of ceramic that's right here at either end, and then we can have the ions that can flow right here, and then you would still have what we call an electrode, typically a piece of metal, and then between that you could put a you could put a light bulb, frankly, and it should light the light bulb up, and you could then, now we have made a battery. So a battery is simply two containers, two beakers or whatever, and these are typically aqueous solutions, and then you've got a couple of metals, and it works.
Yeah.
It's pretty cool,
Two half reactions of a redox.
Yeah. And you have one half reaction take place on this side, and the other half reaction takes place on this side. Typically, it involves the particular metal that you've immersed into the solution.
Yep. Typically, but not always. We'll talk about that.
So now what we want to do is we want to label all the parts of a galvanic cell. All right. So let's actually draw another picture. You're going to find yourself drawing tons of these pictures. All right. So let's take the classic picture. The classic galvanic cell actually came from a guy by the name of Galvani, of all things. Imagine that. Yeah. Whew. We planned that. And you take these little rectangles are pieces of metal. Let's say that this piece of metal is called copper, and this one is zinc. And typically we would then put into this solution some zinc nitrate. Let's say Zn2 positive and NO3 negative. And on this side, I'd put some, say, copper nitrate, copper 2 nitrate. Could be sulfate, wouldn't matter, no difference. Now, what am I missing?
Salt bridge.
Got to have that salt
bridge. And you got to have a wire connecting to your metals, too.
All right, so let's make that kind of a liquid solution here. And then we'll have a salt bridge. This, by the way, is a filled, and it's called a U-tube, actually.
A U-tube?
Because it's in the form of a U, upside down.
But not like YouTube.
Not like U2.
No, or YouTube.
YouTube. Oh, I got it. Oh, yeah.
He's old. It takes him a while.
Yeah, I'm an old man. And then you need a connection, and we'll just put a V here for the voltmeter. All right? All right, so there's our picture. Okay? So we have our picture. Oops. We have our picture here. Looks like the colors went away, Mr. Sams. All right.
Weird.
Oh, well. And so we have, this is a battery. Now I want to label the parts. Now, before we do this, we have to realize what are the half reactions that are taking place. Now, as we're doing, actually, let's come back to this because we need to talk about electrical potential, I think.
Yes, we do.
Don't we?
Yeah, we know which one's the anode and which one's the cathode.
And actually, we have this picture. We'll come back to that picture, so save that for just a moment, ladies and gents.
Coming back.
And there is sometimes, what happens when one of the electrodes is not a metal? okay, you have some problems like that. Let's say you're producing a gas. Some of them do produce gases. What you do is you would have a piece of platinum. You would still use a metal. The platinum doesn't actually react, but it gets immersed into the solution. And this is like an inverted test tube right here on this particular side. And then you can have the gases present, and then the reaction still takes place on a piece of metal. You still have to have essentially a piece of metal immersed into the liquid. But you can do this by having gases present. So this particular reaction is hydrogen, and the hydrogen is going through the solution, and then you can get bubbles coming out and stuff like that. And so that's what you do when you have one of those.
Yep. And by the way, when we talk about the electrical potentials here in a little bit, you're going to see some of them are positive, some of them are negative. Those numbers are pluses or minuses relative to the hydrogen electrode that you see right here. Hydrogen in the electrode is kind of the zero. Everything else is based off of that. And that's how we get those numbers.
So let's take a look at the table. So when we go to the table, this is actually your handout. So this is a very important table. The table is standard reduction potential table that you can see right here. And you can see some values. For example, lithium is negative 3.0. Here's one for lead. And something that's very intriguing about this particular table, we haven't sort of told you this before, I'm sorry. You've always been trying to balance all these half reactions, haven't you? And you know what? Did you know there was a table with all the half reactions in it? Yay. And you didn't have to actually balance them. If you could just find the right half reaction. So there you go. We were lying. So for example, if you want the 10 one right here, I just want this to go away. Okay, if I want the 10, it keeps coming back. Why does it do that? Bizarro. So if I want the 10 one right here, there's the reaction, and there's these numbers, the 0.15, and here's a whole bunch more. It's kind of a busy table. And so this is just your handout, right, guys?
Yep.
It's got lots of different things. And so what we want to do is we want to go back to that one, and we want to look at the different values for the zinc and the copper.
Yep, I saw both of those on the first page.
You saw them both on the first page. Yep. Very good.
So zinc is right here.
Here's zinc. So and we're going to round to probably 2 digits, I think. So here's the zinc one right here. So zinc positive 2. So let's go back to that. So let's go back to this screen, this picture right here. So we have Zn positive 2 plus 2 electrons goes to zinc. And the number for that was negative 0.76 volts. Now we got that off the table.
Yep.
Now we can also have the copper plus 2 electrons. That goes to the copper. And if you look on that table, that is positive 0.34 volts. Yeah, that's right. Okay. Now, what's the problem, Mr. Sams, with these reactions?
Well, they're both reduction. We need one to be reduction and one to be oxidation.
So what do you think we need to have? How would I decide who needs to reduce and who needs to oxidize?
Well, ultimately, you need your voltages to be positive, because if you have a positive voltage, it's a spontaneous reaction. We'll talk about why later.
So what we need to do is we need to flip the top reaction around.
Yep.
So what I'm going to do is write down here is I'm going to write Zn goes to Zn plus 2 electrons. And on this one, I'm going to leave the copper plus 2 electrons goes to copper.
Right.
And if you add these two voltages, that'll be positive 0.76 when you flip it. If you flip it, you multiply by negative 1.
Yep.
And this will be positive 0.34 volts. And this is 1.10 volts. So the voltage, if you had a voltmeter set up in this particular system, it would read 1.1 volts.
Hey, I wonder if that's what this would read if I had it hooked up on my little clock.
I believe so. Yeah. Now let's talk about some more things that are happening in this cell. Now in all galvanic cells, or batteries if you will, there is a positive and a negative side.
Yes, there is.
Yeah, like a battery. You look at a battery, it's got a positive end and a negative end. So we actually give names to those positives and negatives. They're called what?
Anode and cathode.
The anodes and the cathodes. And anodes, oxidation occurs. Guys, you should write this down somewhere.
Yes.
On a blank screen here. We'll just skip this. Oxidation at the anode.
Anox.
And reduction, D-U-C-T-I-O-N. Reduction is at the cathode.
Red cat. Red cat, anox.
Is that how you do it?
Yeah, red cat.
Do you guys always remember? You know, an A and an O are both
vowels.
Vowels.
My
An
son
R
is
and a C, they're both
consonants.
Keep your vowels together. Keep your consonants together. That's how I remember it.
I like red cats.
Okay, it works for you too. All right, so the zinc is being
That looks
oxidized.
like oxidation to me.
So this is called the anode, and this is called the cathode. By the way, the anode has a negative sign, so if we had a battery, and the cathode is positive, because cats are good, or that's how you can know that cats have a cation.
I like cats.
Yeah, I don't actually, but that's a whole other story.
You're a dog person. Oh yeah, that's right.
Have mercy. Now, we still haven't completely labeled this. There's still more to do.
Salt bridge.
What about the salt bridge?
It needs a name.
All right, so let's label salt bridge. Now, since we're actually using the electricity, the electrons have to be traveling through the wire. What is the direction of the electron?
They go from the anode to the cathode. Gosh, I can't talk to the anode. From the anode to the cathode.
You can't talk, the man has bad accent. He must learn to speak English.
Exactly.
Oh my gosh.
It makes sense. If you look at the equation down there, we're producing electrons in the anode. Right. So then they're going to go to the cathode where we're getting the electrons.
Yeah, the electrons leave the zinc cell, and the copper wants them. But of course we have a problem. As the electrons flow into here, it's going to cause the charge of this side to become more negative. And so to counteract that, what's going to happen is through the salt bridge, you must have negative things flow this way. So these will be called the anions in the salt bridge. Now, when I say the salt bridge, typically we'll put like sodium nitrate in there.
Yeah,
so in this case, the nitrate ions would flow through here, actually through here to there. And then conversely, actually, your cat ions
sodiums are going to come that way.
Are going to come this way because it equalizes the charge. So you can see this is a very, very busy picture. What are the kinds of typical things you're going to be asked to solve for? Okay, the kind of things they're going to ask for is direction of electron.
Yeah. Direction of electron flow.
Now I can't talk. D-I-R-E-C-T. Direction of flow of electrons. Also direction of electrons. Direction of flow of cations.
Or anions.
Or anions through the salt bridge.
Or which side is the anode, which side is the cathode, things like that.
So there's lots of questions that you'll be asked on tests, on the AP tests, whatever. They love to ask questions like that. It's just common. All right, the table. All right. Now, how do we actually use this big fancy table that we looked at? All right, the table above, the one that's in your handout, assumes that you have a
1 molar solution.
So when we said it was 1 volt, that assumes that it's a 1 molar solution.
So I guess my little soda pop battery here probably didn't actually produce.
And also 1 ATM and
25 degrees Celsius.
25 Celsius. So we're really not at these conditions.
Nope.
But that's what the table assumes. Later on in a subsequent podcast, we'll learn what to do with when we have different molarities and different temperatures and such. Okay. So now let's just use our table. A little practice. You'll find that the table is very, very, very important in your class. Okay. So the first one we have Na is going to Na positive.
Yepper.
Plus 1 electron. Now what I basically want to do is I want to go to the table. And if I go to the table, I can find out what the sodium where's the exact?
It's in the word.
It's in the second one. All right. So we need to find sodium.
Sodium. There it is.
And look at the voltage. Now it's 2.71 negative.
And that's for the plus ion to go to the metal.
So this one is flipped, so it's going to be positive 2.71. You guys see what I did now? Look at your table. If you don't have your table out on your packet, this is going to make sense. That's in voltages. We haven't learned what volts are. We'll learn later. And the PbO2 is going to Pb plus 2. Now, we don't have the whole reaction, but guess what? Instead of me trying to sit here and balance that equation,
let's just go find it.
Let's just go find the reaction.
Pb... Ooh.
Mr. Sams, is this it right
here? I
here?
got it right there, yep.
And there's the reaction. The voltage is?
Negative.
Is it written the correct direction?
It is. That's the way we're going.
So
oh, wait. You know what? That's not right. We want PbO2. That says PbO.
Oh, my. Mr. Sams.
Almost.
So we take a moment and try and find
another
PbO2. I be PbSO4 over here. No, that's not it. We'll find it. Okay, we find. Of course, we're using a table that may not be from the old podcast.
I think this came from Wikipedia.
It did. We're trying to save. There's a PB one, but that's not the right one.
Where's PbO2?
We'll find
wait. Is that it? What's that alpha?
I don't know why we have alpha.
And there's a beta right above it. But they're both close enough. We'll call it
1.5. 1.5. All right, there it is. We find. All right, so it's 1.5, and it's already written, and this is 1.5 volts. Okay, so what's the total voltage?
Well, we want it to add up to positive.
You know, we should probably write the whole reaction.
Yeah.
So let's do, it makes plus 4H positive, all right?
Yep.
So I'm just copying it from the other table.
Plus 2
plus
electrons.
2 electrons. So I'm just flipping back and forth. Makes plus 2 waters on this side. Now, when we add these, though, so we have to multiply this by 2. So the overall reaction, right, would be 4H positive. We'll have to double the top one, plus the PbO2 plus 2Na makes 2Na positive plus Pb2 positive plus 2 waters.
Yep.
So I have this 2 here.
Yeah.
Do I have to do anything with that?
Well, we distributed it through the equation, but do not confuse this with your thermodynamic stuff.
Yeah, folks, this is a common mistake. If this 2, oftentimes we think we need to multiply this by 2.
We do not do that in electrochem.
No, you just add them.
Yep, just add them up.
And I could get 4.3 volts. This will make a pretty strong battery.
Yeah.
4.3 volt battery.
That's a lead battery. That's what they put in cars.
There you go. That's probably why. All right. And let's do this one. So I have Fe plus 3 goes to Fe plus 2. We probably don't need to look this one up in terms of balancing.
Yeah, we balance
it. So let's go back to our
Now be careful
table.
when you look these ones up that have multiple oxidation states. Make sure you get the correct one.
Yeah, because Fe2 to Fe3.
Yep. We're looking. Okay, see, this is not it. This is Fe2 plus becoming Fe metal, so that's not it. We got to find the one that has the actual numbers that we're looking for.
We don't like that one. So guess Mr. Sam's found an Fe2, but it's not Fe2 to Fe3. I don't see any Fe's. It's going to be on the busy page.
It's going to be in the big mess one. Oh, there it is, right there.
Mr. Sam's has got better eyes than me.
And I just had my eyes dilated. I must be getting my vision back.
0.7. Now, to go to Fe2 is 0.77.
Positive 0.77. I think that's what we have. Yep.
So this is positive 0.77 volts.
There it is.
And then we go to Mg to Mg2 positive plus 2 electrons. And if you don't like that table, guys, there is a table in your book that you can also use.
Right.
So Mg to Mg2 positive is going to be at the top of the list. I'm not mistaken.
Yeah.
First page.
I remember seeing it too. There it is.
So it's going to be
negative 2.
But it's flipped.
Yep.
So it's 2.4.
2.4, but it's going to be positive because it's in the reverse.
Yeah, because it was negative and I flipped it, right? And so the total voltage would be 3.17. And the overall reaction, you would have to double this.
Yep.
And it would be 2.
But that still doesn't change the voltage.
Does not change the voltage, plus the magnesium makes the magnesium 2 positive plus the Fe 2 positive. So if you were to separate these in a cell, put a salt bridge between them, and put a voltmeter between them, you would have a voltmeter that would read 3 volts. Now, you've got 9-volt batteries, though. How's that possible? Actually, if you thought, what would be the best battery that you could possibly make with this table? If you think about it.
Yeah, well, we'd want to take...
You would take the lithium. That would be 3 volts.
With the cesium.
And with the one at the bottom end...
the most positive, yeah. Well, but we're going to have to flip one of them.
Well, yeah, just take the most negative and the most positive, and then you get about 6 volts.
Okay.
Because this is 3 volts positive, and if you flip this top one,
oh yeah, I see what
you would get another 3 volts, so about 6. But I've heard of 9-volt and 12-volt batteries. How's that work?
They just take smaller cells, they hook them up in series.
Yeah, they actually hook them together. So if you have a 3-volt battery hooked with another 3-volt battery with another 3-volt battery, well, then you have a 9-volt battery. So it's actually very, very uncommon to have a cell, a galvanic cell, with more than a couple of volts.
Yep.
So this would actually be a relatively large one that we have right here with 3 volts.
And your 9 volts actually have 6 1.5ers in them.
Yeah, they actually have several cells. All right. Now, we've a couple more examples here. Now, can this happen? Now, when you're doing these problems, as you watch the Answer podcast, the key thing on these, is such and such capable of reducing such and such, is you're trying to get a positive voltage.
Yep. If you get a positive voltage, it's a spontaneous reaction.
And it happens.
If you don't,
you don't.
You don't. So
now we do hydrogen. Hydrogen, and Mr. Sam's alluded to this a little bit before, but hydrogen is an interesting part of the electrode. I don't have to look this one up. I know it off the top of my head, but here it is right here, and it's bolded on your paper. But the hydrogen electrode is 0 volts. It is sort of the standard. It's upon which everything is measured. So basically, you're going to have the hydrogen. This is 0 volts. So if I want to reduce the silver, that means I'm taking the silver to reduce it. You're taking it down to a lower charge, and the only lower charge you've ever heard of is 0. So I'm looking for, on the table, I'm going to look for Ag to Ag0 and find out what its voltage is. Yep. And I think it's up high. No, it's down lower. Because I think it's positive. I know this one. Right. Here's an Ag. It's not the one I want.
Nope. Oh,
here it
right
is.
down. Oh.
Isn't it?
You're right. Yep, you're right.
It's about 0.8 volts.
Yep, 0.8 positive volts.
So it's 0.8 volts. So if it's 0.8 volts,
that's
is that
positive? That's spontaneous.
Bingo.
It's
done.
It's gonna happen.
So that's how we can know that. Just looking for positive voltage. Let's do one more. Is H2 capable of reducing nickel to? So nickel to positive to something lower.
Ni.
So some nickel. So we're going to look, and this is hydrogen, so here's 0 volts.
Now, do we want to go to Ni or Ni plus 1?
That's a good question. Yeah.
Let's look them both up and see what happens.
So nickel, 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 I think it's negative, actually, is my recollection from my memory. So we're looking, look. You may find it first before us.
Not on that page.
Not on page 1. Let's go to page 2.
Oh, there's one.
Mr.
Plus
Sims.
2 down to the elemental. Negative 0.25.
Oh, we have a negative. So negative means negative.
Negative.
So at least to go down to nickel 0 and the 2 electrons, this was negative 0.25. You add that to 0 and you get negative 0.25, and that is just
spontaneous.
Not spontaneous. We should do one that's not hydrogen.
Gonna happen.
Yeah,
oh,
we
here
should
we
do
go.
This one.
Yeah.
So is Fe2 positive capable of reducing VO2 positive?
Yes.
So
now,
if this is reducing this,
you're right. If
this is going
VO2
down.
gets reduced, then Fe has to get oxidized, so it has to go up. And the only thing I can go up to is plus 3.
You never heard of anything other but plus 3. That's higher than plus 2 for iron. So let's do the iron number first.
Down on the jumbled, messy list right there. Positive 0.77, but we're going to flip it, so it's going to be negative 0.77.
So this is negative 0.77. So now we're going to find the VO2 and see if we can get a number that's more positive than positive 77. So he should be a positive number.
VO2. I see VO up there. Vanadium.
Of all the ones I picked. I know it's on another table that you may have in your book, and that's where it would probably be. And of course, I don't see vanadium. Vanadium.
Try the next page up.
VO.
Oh, not wrong one. That's VO plus 2, not VO2.
I wonder if I typed it wrong.
It's entirely
VO2 positive. What do you think?
Perhaps. Let's say you've typed it wrong.
Let's pretend that we typed it wrong, and it was VO2 positive. VO2 positive, that might be my mistake.
Yeah.
And if that voltage, if we look, was 0.34.
0.34.
So 0.3, it is positive, right?
It is, but if we add those together, we still have a negative number.
So our negative number is like negative 0.43, did I do that right?
43, yep.
That's a negative number. So
yeah,
that means,
not going to happen.
No, not going to happen.
Negatory.
At least the VO2 positive. So, yeah, that's not how we're going to work. And I think we've probably belabored that.
I think so.
All right, last example here. Rank the following from strongest oxidizing agent to weakest oxidizing agent. Now, what is that word, oxidizing agent?
Oxidizing agent is the one who does the oxidizing and itself gets reduced. So if it gets reduced, if we look on the reduction potential table, if it has a nice big positive sign, it's going to be a good oxidizing agent.
So what we need to do is we need to use the table again. So Ce4 positive can go down to something.
Yep.
So it seems we need to write a bunch of reactions. Ce3 positive goes to something smaller. And then we can have Fe2 positive. I can say that's going to go to Fe. There's no charge. Fe3 positive can go down to Fe2 positive. I'm writing all the reactions. Mg2 positive can go down to Mg. Mg
can't go down.
Can't go down. Ni2 positive can go to Ni, and 10 can't go down. So we're going to just look these numbers up on the table. So this may take a little bit. So Ce4 positive down to something else. You know, can we do Control F and do Ce?
Probably.
Did not find any.
No, there it is, right there. 2 plus to 3 plus 1.44.
4 to 3.
Oh, we have 4 to 3.
Do we have 4 to 3?
Why don't we just go grab a book and we'll look them up there? It'll be faster than thumbing through here. Let's pause.
All right, so we found from your table, actually from your book, folks. If you go from 4 to 3, what's the voltage?
1.70. It is positive.
Positive.
Yep.
All right. Now the CE3 positive really cannot
I'm actually
go
looking
up.
for that.
I don't think it can go down. So this one is really not capable of going down. So actually, he's going to be negative 1.70 volts. We're going to read the way he is because that is CE3 positive to CE4 positive,
yep.
right?
Yeah, I don't see anything else for CE in here.
All right, how about iron 2 to iron 0?
Iron
Sam's is looking
2.
It's over here.
Yeah. Oh wait. No,
well, she found the iron 3 to
iron 2 down to 0 is negative 0.44.
Okay. How about 3 to 2?
3 to 2.
Iron 3 to iron
0.
There it is. First column. There it is, right there.
There it is. Yep, 0.77.
Is it 3 to 2 or 2 to 3?
That is 3 to 2. 0.77.
So positive 0.77?
Yep.
Okay. How about magnesium?
Magnesium. Yep. 2 plus down to elemental is negative 2.73.
Negative 2.73. And actually this one will be
positive 2.73.
Positive 2.73. Nickel, 2 to nickel?
Nickel. 2 to nothing is negative 0.23.
Negative 0.23, not 2.3, and then tin.
Tin plus 2 down to elemental is negative 0.14.
So this will be positive 0.14.
Positive 0.14 if we're going elemental to something else.
Okay. So we want the things that reduce. Now let's think about this. Do we want to go from the lowest number to the highest number, the highest number to the lowest number, the way it's
highest number to lowest number?
I think we're the highest number. So
yeah.
Who's the highest value I got?
Magnesium, 2.73.
So let me change colors and we'll rank them. How about that? So this will be number 1. Number 2 looks like it's the cerium one. All right, more positive ones. 0.77 looks like he's in round 3. I see another positive one, so that would be the 10 would be in 4th place.
Yep.
And the next place would be the nickel, 5th, right?
Yep.
6th and 7th.
There you go.
So you just rank them. Oh, and then 8th for this one. So that's how you do it. You're just going to look it up on the table. You're going to find, folks, that table is your friend.
Oh,
You've got to have that table, and you're not going to memorize it.
No,
You'll always be given
that's
it.
given to you on the AP test.
Yeah, so you just have to know this table. And this is the table of all of the reactions.
Yep.
Okay? Any questions? Please feel free to ask. That is actually the end of the podcast.
Yay.
So we're going to say ta-ta for now.
Toodaloo.
Adios, amigos.